All right, so let's run through the quiz. So good work on the quiz. So you will see combinations, permutations, pigeonholes on the final exam. So I want to run through this and just sort of make sure we're good on it. So question 1, largest number of people who can have 3 unique initials, letters A through Z. Okay, A through Z, there are 26 letters. About 10% of the class thought there were 27, which would be great if we were starting from 0 or something, right? Doing one of these indexed array kinds of things. So I didn't take off for that.
They just know about extra letters.
Yeah, that's a secret letter. So 3 unique initials. So I worded that ambiguously, unfortunately. What I meant was people whose initials are different from somebody else's initials. Okay. I did not mean that this would not be legal, right? That you can't have the same letter. But that was ambiguous. So if you thought this had to be unique initials, you got credit for it anyway. So if you allow things like this, right? This is it's a product rule, right? How do you pick initials? Choose first initial, choose the second, choose the third. 26 ways to do each of those. That's 26 to the third possible names. And if there's only 26 to the third unique sets of initials, then that's the most people that you could have in a room and still have everybody have their own initials. So that's the largest number. That's kind of a bit of a pigeonhole thing there at the end, but it's mostly just logic. If you don't allow repeats, right, then this is number of ways you can choose 3 things from 26, paying attention to the order, which is just 26 times 25 times 24. So either of those were good answers. If you started trying to do this with pigeonholes, with trying to think of 26 bins, it probably took you in the wrong direction. But you can think about it with one initial, right? If you only look at first initials, how many people can you have in a room? Pigeonhole principle would say, for example, once you have 27 people, you're guaranteed 2 people have the same initials. 27 being one more than 26. But if you look at pairs of initials, how many people would you put in a room to guarantee that at least 2 of them have the same pair of initials, right? You have to know how many different pairs of initials are there. And that's, 26 squared or 26 taken 2 at a time. And then pigeonhole principle says if you had one more than that, you'd have a guaranteed duplicate. So does everybody understand those 2 answers? Right, repetitions allowed, no repetitions allowed. But it's a product rule. If you add 26 to itself, you're doing a sum rule. So, all right, so question 2, password questions. These are always good fodder for final exam questions. That's a hint. Uppercase letters, 4 uppercase letters, no repeats allowed. Okay, so 4 letters, no repeats. So pick the first letter, 26 ways to do that. Pick the second letter, it can't be the same as the first, so you only have 25 options. Pick the third letter, pick the fourth letter. So that's repeats not allowed, which is just 26 comma 4. That was question B. Question A, repeats allowed. That's like the initial question, right? So that's 26 ways to pick the first, 26 to pick the second, and the third, and the fourth. That's 26 to the fourth. So part A, 26 to the fourth. Part B, 26 times 5 times 4 times 3. Okay, part C, 4 letters, has to start with a Z and no repeats. Okay, you can always product rule these things. If you can't remember combination, permutation, that kind of stuff, think of it as a product rule. How do we pick a 4-letter password that starts with a Z? Pick the second letter, pick the third letter, pick the fourth letter. Okay, this letter cannot be a Z because no repeats are allowed, so there's 25 ways to fill in that second letter. And now we've used 2 letters, so there's only 24 ways for the third letter and only 23 ways for the last letter. 25 times 4 times 3. Alright, 6 letters must start with ZQ, no repeats allowed. So your password looks like ZQ, followed by 4 other letters. So how many ways can we choose this first unknown letter? 24, right? Because we can't pick a Z or a Q because there's no repeats allowed. So 24 times 23 times 22 times 21. Or P24, comma 4. Alright, E, no repeats allowed. 6 letters must begin with a Z or a Q. This is a sum rule. As soon as you see or, think about sum. Can begin with a Z or a Q, so we have 2 possibilities. We can form a password like that, or we can form a password like this. Alright, well, 6-character password starting with a Z, it's kind of like question C, right? How many ways can we fill these in? This is just 5 things chosen from 25. And if we start with a Q, this can be filled in however many ways. We can take 5 things from 25, paying attention to order, and so we add those together. And so this is 2 times 25 times 24 times 23 times 22 times 21. Alright, and then the chicken race. 6 chickens, no ties possible. How many finishing orders are there? Well, we're picking an order of 6 chickens taken from a set of 6. It's just P66. So that's just 720. Alright, I decided I kind of hated that 4th problem. I thought it was a good idea at the time. But it was good because I saw lots of good thinking about it. And that's what I was after. So, but let me show you how I was thinking about it. So you're picking 8 numbers between 1 and 10. And you want to know how many times will the set of numbers that you picked, how many pairs in that set will add up to 11. And you could pick, for example, 1, 2, 3, 4, 5, 6, 7, 8. And how many pairs add up to 11? Well, 3 and 8, and 7 and 4, and 5 and 6. We got 3 pairs that add up to 11. All right. I could have done this. And now I'd have 4 pairs that add up to 11. Well, 4 is the largest we can get, right? Because we've got 8 numbers, we've only got 4 pairs. So that's the most. We know we can also get 3. Is it possible we could pick 8 numbers and only have 2 pairs add up to 11? I don't know. So that's what the question's asking is what's the minimum number of pairs that'll add to 11? And the answer does turn out to be 3. But you can prove it using Pigeonhole Principle. So make yourself a set of buckets. We'll have 5 of them. Well, if I pick 5 numbers, I can put numbers into each bucket and have no repeats. But the way I've labeled these buckets is if I have 2 numbers in a bucket, they will add up to 11. Okay? So I could pick my first 5 numbers, they might all go into separate buckets, but I know that if I pick 6 numbers, at least 2 of those numbers are going to add up to 11. Possibly more. But at least 2 of them will add to 11 because by the pigeonhole principle, at least one of these bins will have at least 2 things in it. Right? And once I have 2 things in one of these, those 2 numbers add to 11. So 6 numbers, at least 1 pair adds to 11. Okay, well, I don't know which pair, but let's just say it was that one. Let's get rid of that bucket. And so now I have 4 numbers. And 4 buckets. Sorry, I have, okay, so I start off with my 6 numbers, put those in, okay, got rid of 1 bucket. I have 2 new numbers to add in, right, so I'm going to have 8 minus 2. I'm going to have a total of 6 numbers with 4 buckets. Pigeonhole principle again says at least 1 bucket is going to have 2. So now I've got another pair. So whichever one that was, throw away that bucket. Okay, I picked 8 numbers, I've thrown away 4, I have 4 numbers left. Placed into 3 buckets. Pigeonhole principle kicks in once more. I have at least 1 pair. Right, 1 bucket containing 2 entries. So throw away whichever bucket that was. Now I've thrown away 6 numbers, I started off with 8. I have 2 numbers left and 2 buckets for them to be placed in. It's possible they could go into separate buckets. No pigeonhole principle. So we have 1, 2, 3 pairs guaranteed. Could be more, but there's got to be at least 3. So that's one way to think about it, but I saw lots of other explanations. All right, so other than the weirdness of question 4, any questions about combinations, permutations, pigeonhole, binomial theorem, passwords, chicken races?
No, sir.
No, sir. All right. All right, where did we leave off on Friday? We were constructing grammars. How far did we get with that? Anybody remember?
We should just restart.
Just start from what is a set?
Yeah. This was the last week.
Oh, excellent. Ah, okay, cool, good, thank you.
What's that? Yeah.
So let's look at a language like the set of all strings containing 1 or more zeros. So my start symbol will be S, my terminals will be 0, 1. Actually just zeros would work. And my vocabulary will contain 0 and 1 and maybe some other stuff. And let's look at the production rules. So we want to go from the start symbol to something and make some rules so that we can generate strings of length 1 or more comprised of only zeros. So what could we do here? Okay, I'll start here. We could go with S to 0. That would get us our string with 1 0 in it. But this is going to have to be a finite set, so I can't just say S goes to 0, 0, S goes to 3 zeros, and so on. We need something more general.
0S.
S goes to 0S. So now S could become a 0 followed by an S, where that second S is a 0, that gets us 2 zeros. Or S could go to a 0 followed by an S, which is a 0, followed by an S, which is a 0, that gets us 3 zeros. So yeah, this should get us everything we need.
Do you need a S to lambda as well?
If we wanted to allow the empty string, yes. But since n is bigger than or equal to 1, this has to be at least 1 0. So we're just not having the empty string. If this was bigger than or equal to 0, then yeah, go to lambda. Here's another way we could do this. I could have S go to 0 followed by an A, where an A is understood to be 0 or more zeros. And so A can be the empty string, or it could be a 0 followed by an A. That's a slightly more complex production set and uses another symbol. But it's just a different way of thinking about it. Suppose we wanted 1 or more zeros followed by a 1. Yeah. That's just the language generated by the grammar.
Okay.
I just like writing it.
Map S to A1 and map A to 0 or A to
So map S to A1.
A to 0.
All right, so S is an A followed by a 1, where A is either a 0 or a 0A. So we're basically using the production rule that we had up here for a string of 1 or more zeros, but instead of changing the start symbol in that, we're changing an A into that. And we're changing the start symbol into that string of 1 or more zeros followed by a 1. Everybody like that? So these take playing with, right? There's homework questions, so mess around with them, but it's you know, trying to bridge from analyzing, which is pretty straightforward, to synthesizing, which is mysterious. But becomes less mysterious the more you do it. Yeah.
So does the order like the ordered ladder shows up as 0, 1 to 6, and 0, 1 to 0?
No, those are different strings. So like here, for example, or so these are strings. So yeah, the order is significant. Think like a string in C. Okay, that's what we're talking about. All right, other questions? All right, so that's one way to deal with syntax, is to describe something like a phrase structure grammar. And we can take a string and we can say, is it generatable by this grammar, right? Or we can use the grammar to generate strings. And applying these productions to strings, we can write code to do that pretty easily. All right, so there's another approach which is called BNF, which is Bacchus-Nauer form. And this is kind of like what we started off with diagramming sentences. A sentence is a noun phrase followed by a verb phrase. That's the kind of thing that BNF does for us. So let me give you an example of using BNF. So we have some symbol over here, colon equals equals, and then we say what it's equal to. So this is the BNF for what I'm calling an assignment statement. That's what AS stands for. So an assignment statement is a variable followed by an equal sign followed by an expression. Okay, it's like sentences, noun phrase followed by verb phrase. So an assignment statement, and I'm thinking in like C or something, is a variable followed by an equal sign followed by an expression. An expression I'm going to define as either an expression followed by an operation followed by an expression, or, and the vertical pipe is an or, a parentheses followed by an expression followed by a closed parentheses, or a variable or a number. A variable is a letter followed by a variable or just a letter. So you can have variables with letters in them but not numbers, just because it makes it a little easier. A number is a minus sign followed by an unsigned number or just an unsigned number. An unsigned number is a digit followed by an unsigned number or just a digit. And an operator is a plus or a minus or a times or a slash. A letter is an A or a B or a Z, 26 or 27 options. A digit is a 0 or a 1 or up to a 9. Okay, so what does all this mean? This is a way we can diagram something and say, is it an expression? So let's look at an expression and see what this does. So sum equals sum plus in. Okay, this should parse successfully as an arithmetic assignment statement. Why? Sum would have to be a variable. There's an equal sign. Sum plus in would have to be an expression. Okay, what's a variable? It's a letter followed by a variable. Well, SUM is an S followed by a UM. UM is a variable because it's a U followed by a variable. M is a variable because it's a letter. Okay, so this is capturing our notion of what is a variable. It's a collection of uppercase letters, right, where you have to have at least one letter. So sum is a variable, plus is an op, in is also a variable, so sum plus in matches the pattern of an EXP, an expression, which means this whole thing matches the pattern of a variable, an equal sign, and an expression. So if I had a piece of software that knew this BNF for an assignment statement, it could take this string and come back and say 1, true, this is an assignment statement. Whereas if I did something like this, right? This is a variable, this is an equal sign. Is this whole thing an expression? Well, sum is an expression, plus is an op, is in star plus z an expression? Well, in is an expression, star plus z, star plus is not an op, right? It could say star is an op, but then plus z would not be an expression. And no matter how it tries, none of these descriptions of an expression is going to match this whole thing over here. And so this string will not match an arithmetic assignment statement. So the parser would come back and say, no, that's not consistent with the BNF for an assignment statement. And BNFs are fun, yeah.
So, where is this, like, information stored?
It's a good question. It depends on what you're using. So there's a ton of tools out there that will ingest BNF and take a string and tell you if it conforms to it or not. So there's Unix tools like Lex and Yak are two big ones. I think Bison to some degree that you can feed this information into and it will use it to check syntax. Or you can write your own. Or you can transcribe it into something else. So, let's see if I can find this quickly. So when I first encountered BNF, it like changed my world because suddenly I had a way to grasp the idea of syntax, and before that it was just nebulous. Like, how do you describe the syntax of something?
This is kind of where you get into like bootstrapping and like when you're first creating a system with Oldwood.
This is where you would get into things like writing compilers,
Okay.
right? So, yeah, I should have done this ahead of time. Because this basically lets you, I'll do this another time. This basically lets you do things like say, give me a program and let me know if it's valid syntax or not. But the thing is, while you're going through analyzing the syntax, you're also breaking down the input, right? Once I've decided this is a variable, an equal sign, and an expression, right? If while I was matching a variable, I saved this string sum somewhere, right? And if I save this expression in another string, right? Now I can pass this to something like my stack-based calculator, right? And generate code that will evaluate my expression and then store it wherever I'm storing sum. And so you can build up compilers using this, right? So you can look for things like the BNF for C. And it's not that big. Right? That's the whole C language.
I guess that's not too bad.
That's not, and there's a lot of stuff in here that we don't usually talk about in these classes, like unions, for example. But you know, you can use this to analyze a set of text which is in a .c file and understand what it's asking you to do. Right? C is a simple language. It has very little to itself other than function calls, assignment statements, arithmetic expressions, arrays. But there's all of this stuff for, you know, different types of operations, shift operations, and so on and so forth. This also almost magically handles parentheses. If you ever try to parse a string that has parentheses in it and figure out what exactly gets done first and next and so on, this actually takes a lot of the pain out of it. So anyway, I have some C code somewhere. I'm not going to go through it right now. That lets you do this kind of thing. If you're interested, catch me offline, and I'll share it with you. So you have a question on the homework to write the BNF for a floating point expression. Okay, so my goal is just to kind of think about it and play around with this sort of representation. And it's a very simple structure, right? Symbol, colon equals equals, and then you just list what it can be. Use pipes to separate things by an or. And there's, you know, terminal symbols, like digit is just one of these 10 things. Or you can include other things that are themselves defined elsewhere. And it can be recursive, right? So a variable includes the notion of a variable, expression includes expressions, and so on. All right, so let's talk about state machines. State machines are really useful for parsing and studying languages and breaking things down. Everybody here taking Engineering 250? Yay! Okay, so if you've done 250, we've done state machines in there. If not, this is the first introduction to state machines, perhaps. So what's the idea? We have states.
Oh, it's a state diagram. I remember this.
But I won't draw state tables. Those are. All right, so there's a state diagram. We have 4 states, S, P, S, P, C, and C, and we have 1 input, and maybe 1 output. So state is, something about your system, a collection of variables in memory, something about it. And these arrows show how you can move from one state to another. So from the S state, we could stay in the S state, or we could go to the PS state. Okay? And the arrows are tagged with something / something. So the system has an input in this case. It's a single bit input, which is a 1 or a 0, and it has a single bit output. And so if you're in state S and your input is 0, this says we should generate an output of 1, but change to state PS. And if you're in state PS and your input is a 1, we should generate a 1 for the output and change to state S. So a state diagram describes the behavior of this system called a state machine. And basically you have inputs, you have outputs, you have states. And there's a notion of a clock underneath all of this. When the clock ticks, your inputs are analyzed, and based on your current state and your inputs, you move to a new state, possibly the same state, and you generate outputs. Okay, that's a very general state machine. And so this machine is sitting inside your laptop CPU, most likely. A machine that does these kinds of state transitions. This is a weather predictor. Okay, this tells you what tomorrow's weather is going to be based on today's weather and whether today is sunny or cloudy. So our input looks like this. 0 equals cloudy, 1 equals sunny. And that's also what the output value means. It means tomorrow will be cloudy if it's a 0, sunny if it's a 1. And we can think of our states as this: sunny, probably cloudy, and cloudy. Okay, so how does this work? We're sitting right here, it's sunny outside. Okay, so if the sun is out, we're going to stay in the state S, and we're going to say that tomorrow's weather is going to be sunny. Okay, this is the best way to predict weather, just repeat today's weather. Okay. If we've been predicting that it's going to be sunny, but it's actually cloudy today, we predict that tomorrow it's going to be sunny. Because if it's sunny for 5 days in a row and then there's one cloudy day, maybe it's just a fluke. Right? So we're still going to predict that it's sunny, but we're going to move to the state PS, which is like probably sunny. Okay. But if we're in this state and it's cloudy tomorrow, right, if our input is a 0, we're going to change our prediction. We're going to say the next day is going to be cloudy, and we're going to move to this new state PC, which says it's probably going to be cloudy. So basically, this is a state we're in where it's been sunny for a bunch. This is a state where it's been cloudy for a bunch. If it's been cloudy for 5 days in a row and we hit one sunny day, we'll come over here to note the fact that we had a sunny day, but we'll still predict it's going to be cloudy. If it's sunny again the next day, now we're going to move up here and we're going to output a 1 saying, okay, it's probably going to be sunny tomorrow. It takes 2 sunny days in a row to change our prediction. It takes 2 cloudy days in a row to change our prediction. So that's a state machine for predicting the weather. Works better on the East Coast because we have jet stream effects we can track all the way across the country. Out here it's kind of random seeming. This is also how you can predict whether a conditional branch is likely to be taken or not. That's the part that's used inside CPUs. So when you have a conditional branch if x is equal to 0, we don't know the value of x ahead of time. But if you can accurately predict whether that branch is going to happen, you get faster execution of your instruction stream. Okay, if you've done 270, this is the whole deal with branches, and sometimes they take 1, 2, or 3 instructions. So branch prediction is critical in modern CPUs. It's the only way you keep your CPU time up. And this is a machine that will do a pretty good job of predicting whether branches are taken. Basically, if your branch is taken 2 times in a row, you're going to predict next time it'll be taken. And if once it's not taken, you're still going to predict next time it will be taken. And if twice in a row it's not taken, then you change your mind and you say, okay, it's not going to be taken. This works really well for nested for loops, which is probably the most common case where you have conditional branches. And if you have a nested for loop, you keep taking the branch over that inside loop until you get to the end of that inside loop, and then one time you don't take the branch. But if that whole thing is in a big loop next time through, in fact next n times through, you are going to take that branch. So this does a good job predicting in those situations. So state machines are our friend. And if you do this in 250, you make big long tables and you build circuits using flip-flops, or you analyze circuits containing flip-flops to bridge from a state diagram to hardware. We're not going to do that. We're going to stick to working with just state diagrams.
Thank you.
Yeah, you're welcome. But we're going to look at some of the things we can do with this. So for example, here's a 2-state system. States S1 and S0. And 1 input and 1 output. And I'm going to put a star next to the initial state, so the state that the system starts in. And so our input is a string of 1s and 0s, and we can ask what output this produces. So let's say our input is 1 1 0 0 1 0 0 1. Okay, we're starting in S1. What happens when we get this first input of 1? Moves to S0 and we output a 1. Okay, S0, we get an input of 1. What do? We go back to S1, but we output a 0. Now we get a 0, so we're going to output a 0 and go to S0. And we get another 0, we're going to output a 1 and go back to S1. Okay, S1 and a 1, we're going to output a 1, go to S0. S0 and a 0, we're going to output a 1, go to S1. S1 and a 0, we'll output a 0 and go to S0. S0 and a 1, we'll output a 0 and go back to S1. So how does the output compare to the input? It's different. It's not obvious, right?
Just shifted one, isn't it?
I don't think so, because we got 3 ones here in the middle.
Oh.
But let's look at the state diagram. What is the state diagram doing? First of all, how are we changing from state to state? What's the pattern here? If we're in state 1, what's our next state going to be? Does it depend on the input? All right, if we're in state 1 and the input's a 0, what's our next state?
S0.
If we're in state 1 and the input's a 1, what is our next state?
S0.
Okay, so S1 always goes to S0. Once we're in S0, what's our next state going to be after that?
S1.
It's guaranteed. You're either going to go here or here, or you're going to go to S1. We're just bouncing back and forth between 2 states. Yeah?
When
This, so input slash output. All right, so if we're in S1 and we input a 0, our output's a 0. If we input a 1, we output a 1. So when we're in S1, we copy the input to the output. What do we do with our input if we're in S0?
Invert it.
We invert it, right? So this whole thing is a machine that basically toggles the 2nd, 4th, 6th, 8th, all the even numbered bits. So this one, this one, this one, this one got toggled. So it copies the input to output, but it toggles every other bit. Not necessarily a very useful thing to do, but that's what it does nonetheless. So we can do string manipulation using state machines, but we can also do string recognition. So here's another state machine. Here's state S0. That's your initial state. Here's S1, here's S2. And I'm going to draw 2 circles around S2. And that's going to be our symbol for what we call a recognized state. Okay, the star means that's our initial state. And we're just going to have inputs here, no outputs. So I'll just draw arrows with values on them. All right, so here's the idea. You have a machine, you feed an input string to it, you start in the initial state, and if you end up in the recognized state, then that string is said to be recognized by the machine. In other words, it's considered to be syntactically correct, for example. So what string starting from S0 will take us to state S2? Almost. So 0. So the string 0 is recognized. What else?
1, 1 or 1, 0.
1, 1 will take us there. 1, 1. 1, 0 will take us there. Empty string would leave us in state S0, so that's not recognized. And then what else?
Any 1 or 0 appended to that.
Yeah, any of these with 1s or 0s appended to it. Right, so almost anything is recognized by this. In fact, I think the only thing that's not recognized by it is the string 1 or the empty string. All right, so let's make it more interesting. So here's our initial state. Here's our recognized state. So what kind of strings will be recognized by this? Okay. Because 0 will take us straight to S1, that's a recognized state.
0, 1.
0, 1.
0, 1, 1. 0, 1, 1.
So 0 followed by any number of 1s. Good. Anything else?
0, 0, 1.
0, 0. That's not
Three,
recognized.
3, 0.
But 3 zeros would. 0, 0, 0.
Oh, I see.
0, 1, 0, 0, 0, 1, 0, 0.
1, 0.
1, 0.
1, 0, 1. 1, 0, 1, 1.
All right. So you play with this, right? You throw some strings in, you get a idea of it. We're starting to see there's a lot of strings. We can't list them all. So let's think about what this machine is doing. If you're in your start state, what's the description in words of what's going on?
If 0, then branch. If 1, stay.
If 0 branch, if 1 stay, right? If we start getting in 1s, we don't do anything. We stay in state S0. So leading 1s seem to have no effect. But once you get a 0, you go to the recognized state. Okay, if you're in the recognized state, what happens if you get 1s? You stay recognized, so they seem to have no effect there. So 1s don't seem to have a whole lot to do with this. But if you're in the recognized state and you get another 0, what happens? Back to S0, which isn't recognized.
So only zeros really matter.
So only zeros really matter. Okay, so let's just look at the zeros. So what's the synopsis? When is a string of zeros recognized?
It's odd number of zeros.
It's an odd number of zeros. So first 0 will take you to a recognized, and then you have to get 2 more to come back. And the 1s don't have any effect. So any string with an odd number of zeros will be recognized by this. If you wanted an odd number of 1s, we could just change around the 1s and the zeros. Okay, what if we wanted a single 1 followed by a string with an odd number of zeros?
I mean, whatever we want.
What if we only wanted to recognize a string consisting of a single 1 followed by an odd number of zeros?
Add another section in the middle.
Okay.
And then have that be. Oh.
So let's make a new start state and let's look for that 1 in the beginning. And if you find a 1, we can go down here and look for an odd number of zeros. If you find a 0, we'll stay here. Well, that's not quite right.
Couldn't you just make the same 0 connections to S1 as the previous start?
Except that if you don't start with a 0, we don't want to recognize you at all.
Oh, so you need to start with a 1.
Yeah.
And then, okay.
So how do we find something that has to start with a 1? Let's just recognize any string that starts with a 1.
You could do that same thing, but it needs to stay S1 where it starts with 0.
Cool. So we'll have a bad state. We start in state S. If you have a 0, we go into your bad state, which will always stay there. If you have a 1, we could go to this state, and this machine will now recognize a string with an odd number of 1s. So we can piece these things together, which is kind of cool. All right, so state machines can be used to transform strings or to recognize strings. And if we wanted to, right, we could design hardware to implement such a machine. It's easier to do in software. And in fact, when you try to write software to process something like BNF, you're really writing a state machine. So this is underpinning a lot of what we do. All right, so let me talk about a very particular type of state machine. This is called a Turing machine. Okay, Turing machines are basically the things you have sitting in front of you on your desk or carried around in your pocket or sitting on your desk. They're today's computers. They're basically Turing machines. So Turing machines were dreamed up, almost 100 years ago as a theoretical model of computation. People were trying to understand what can and cannot be computed using some sort of machine. And in order to do that, we needed a model of, what does it mean to perform an algorithm? What kinds of things can we ask a machine to do? And so a Turing machine was invented as a theoretical machine that eventually turned into hardware. So here's what a theoretical Turing machine looks like. We have an infinite strip of tape sitting on two spindles. And you can think of magnetic tape if you like, or it could be paper tape with holes in it. But a piece of tape on which we can write symbols, okay, in some way. And some way to read and write symbols from that tape. So a read-write head. And in a real theoretical Turing machine, the tape would move left or right. Right? But when we do this on paper, we usually think of the read-write head as moving left or right. So we'll think of the tape moving for a few minutes, but eventually we'll switch to moving the read-write head. So this tape has different things written on it, different characters or digits or binary bits or whatever. And you can read what's under the read-write head, one character at a time, and you can also modify it. And you can say, I want to move one spot to the left or the right. Okay? And the whole thing is driven by a giant state table. And so your state table looks something like this. Current state, value under the read-write head, new state, value to write to the tape, and whether to move to the right or to the left. And you have potentially a number of these operations. So here's a state table with 6 entries in it. And you have an initial state, which is understood somewhere, so maybe S0 is the initial state. And so this looks like current state. Symbol, next state. What you want to write to the tape, and which way you want to move. Okay, so we start off in state S0. Here's the deal. We read the symbol on the tape under the read-write head. And we look for a rule that matches our state and the current symbol. Okay? This is state and input from 250. Okay? So if we're starting off in state 0 and we read a 0, this is the rule that applies. And it says we should change to state 1, we should write a 1 on the tape, or we should move to the right. If instead we're in state 0 and we have a 1 under the read-write head, we should move to state 1, we should write a 0, and we should move to the right. If we're in state 0 and there's a blank under the tape, we should move to state 1, write a 0, and move to the right. If we're in state 0 and there's something else under the tape, read write head, which doesn't match any of our states, the machine halts. If we try to go to a state like S2 and there is no rule for S2, the machine halts. Okay, so anything that it doesn't know how to respond to, the machine just stops. And that's it, it's off. So the question is, by writing these state tables and having different initial things on the tape, what can we do? Can we do anything useful? So let's just play with mechanics for a few minutes. Let's suppose our tape contains a bunch of blanks, and then 2 zeros, 2 ones, and a bunch of blanks. And let's suppose we're initially looking at this 0. And we're starting in state S0. Okay, so we need to find a rule that says we're in state 0 and we have a 0 as our symbol. And there's one rule, it's this one right here. So it says we should replace that symbol with a 1. We should move to the right, and we should go to state S1. Everyone got that? Okay, so now we're in state S1, and we have a 0 under the read write head. So we're looking for a rule that says S1 0, that's this rule right here. It says replace that 0 with a 1, move to the left, and go to state S2. So now we're in state S2 and we have a 1 under the read write head. We look for a rule that says S2 comma 1. There is none, we halt. Okay, and what this system has done was it changed our 0011 into a 1111. That's all it did. All right, suppose our tape started off with a bunch of blanks and then a 101 in the middle, and we were sitting on top of that 1 to begin with. Okay, we're in state S0. So we want a 0 comma S0 comma 1, that's this rule right here. It says replace that with a 0, move to the right, and go to state S1. So now we're in S1, we have a 0. That says replace that with a 1, move to the left, and go to S2. So now we're in S2 with a 0, and there is no state, we stop. So we changed our 101 to a 011. I suppose our string contained a couple of 1s, a space, a 0, 1, then a bunch of spaces elsewhere. So we start in S0 and we have a 1 that says write a 0, move to the right, and go to S1. S1 with a 1 says write a 0, move to the right, and stay in S1. Now we have S1 with a blank, which says change that to a 0, move to the left, and go to S2. Now we're in S2 with a 0, there is no state, the machine halts. So a pair of 1s followed by a blank changed into 3 zeros. So this is a really quirky kind of system, right? It's like really crude, but you can actually start to do useful things with this. For example, suppose we weren't sitting on top of our 1 over here. Suppose we were sitting, you know, somewhere over a bunch of blanks. And we wanted to move to the right until we got to our first digit, right? We can make a state table for that. So here's how I would think about it. Let's start off with state 0, And if we have a blank, let's stay in state 0, let's write a blank, and let's move to the right. Well, this is going to basically move me all the way over until I get to something that's not a blank. And then if we're in S0 and there's a 0, we'll go to state S1, we'll leave a 0 there, and we'll move to the right. And if we're in state S0 and there's a 1, we'll go to S1, we'll write a 1 there, and move to the right. So now we've moved all the way over until we got to something which was a 0 or a 1. We left that digit unchanged, and we moved one spot over to the right. And we went to a new state, S1. So if we're in S1 and there's a 0, I'll move to S2, I'll leave a 0 and move left. If we're in S1 and there's a 1, I'll move to S2, leave the 1 and move left. So what's happened now? Whatever digit we found under this arrow, we rewrote that digit on the tape, but we moved left one spot. And so now in state S2, we're sitting on top of that first digit. And now we could do, if this was something useful, we could do these states, name it S2, and so on. So you can actually start putting together useful things with this mechanism. And so this was the theoretical model of computing that was used by Alan Turing and others to study questions of computation. So you can find Turing Machines simulators online. So this is my favorite, I think. And so what is this doing? This is looking for palindromes. Okay, so it's not a horribly long program. It's got comments in it, right? So, and there's some shortcuts in here. There's some wildcards, and there's fancy state names and so on. But it's basically doing the same thing, right? And you can load in an initial string. And run this, and it will go through and figure out if it's a palindrome. And then if it is, it gives you a happy face. I don't know what it does if it's not. Hopefully it doesn't like burst in. Oh, that was pretty fast. Right? How the heck would you do that with a Turing machine? Well, we know how to find the first digit, right? We know how to find the first digit, right? Just keep moving over till you get there. And then, if that's a 1, we could go to one state, so we can remember it was a 1. If it's a 0, we can go to another state, and then move over until you get to a blank on the right. And once you get to that blank, back up one spot. Well, if we're in the state that said we found a 1, see if that's a 1. If it's not a palindrome. So we go to another state which will print the frowny face. But if it is a 1, or if we noted that we had a 0 and this is a 0, now what can we do? Well, we can replace this with a blank. We can move back over here, replace this with a blank, move over one spot, and just repeat. And if we get to a spot where we're checking one digit and the character immediately to the right is a blank, we're done. And so we go to the state that prints out a happy face. And Turing machines turn out to be universal. So we can load example programs from here. So here's binary addition. So pick two small numbers that I can convert to binary in my head.
4 and 6.
4 and 6? Okay.
7. 4 and 7.
4 and 7, okay.
So,
All right, so 0, 1, 0, 0 and 0, 1, 1, 1. And let's load those in. And let's run it. So 4 and 7 should be 11. And so it's writing temporary symbols out there, and there's 11.
whoa.
So multiplication. There's 4 and 7. Let's run that. And we can run at full speed. So there's 28. Total number of steps, 253. All right, so let's do the primality test. So let's see if 7 is prime. So now we're doing division, and we're incrementing by 2, and we're doing something to know if we get past the square root.
That's a lot of steps.
And yeah, so we just hit 2,000 steps. And it's prime 2,600 steps later.
Is that in base 10, or is that actually decimal?
That's binary. Yeah, so here's 1001, that's 9, should not be prime. So that's taking a little more work. So that's not prime.
You know, are all those temporary symbols, like each temporary symbol means the same thing? Like if it doesn't x, each x means the same thing as the previous x?
I don't know, I haven't reverse engineered this code. So this program is a few hundred lines, a few hundred states, and not very well commented.
What grade would you give that?
Yeah, I don't know, that's a hard question, right? Because it's brilliant, but not documented well. And they didn't put their name on it either. But yeah, I mean, you try to imagine doing something like addition, and addition is not that hard to imagine, right? How do you add 2 digits? Well, so add 9 and 11, right? So start off from the end and move until you get to a blank, back up, that's your first digit. Go to one of 2 states based on what that is, and then move over till you get to another blank, back up. Well, you know you had a 0 or a 1, you know what your current digit is, and you need another state eventually for whether you've got an incoming carry. So you've got 8 states possibly. And when you look at this bit, right, you can decide based on your state, based on what the previous bit was and whether you had an incoming carry, what the new value should be that you're going to write out for the sum, and what your new state should be. Do you have an outgoing carry or not? But the only memory you have is this tape, right? So as I'm producing my sum, I need to do that somewhere. So I would probably do that, you know, after this last blank. But if I need to have multiple things written on my tape, one way to do that is by writing temporary symbols. So I might write an X for this variable I'm calling X and a Y for a variable I'm calling Y. It's a very different way of thinking about programming. But once you start messing with it, it becomes really sort of second nature at some point. And then your brain is starting to shift. So there's a Turing machine question on the homework. I will not grade that one, but please try it, okay? But this was extremely rushed. And I want the homework in on Wednesday anyway, so I can get it back to you Friday. But I won't grade the Turing machine one, but give it a try anyway and start messing with it. So we'll talk more about Turing machines on Wednesday, and we'll talk about some of the fundamental questions related to them.
What days are the
There's only one final for this course, and I believe that's going to be Monday at noon. But double check. And the other ones are Monday and Wednesday. But double check Canvas, don't trust my memory. All right, I'll see you next time.